Good morning. Top of the morning to you. Molly, lights good or no? They're good now? Okay. All right. So, looking ahead to this week, today we are going to do some arc length, radian measure, central angle type things. Couple of key things to do there. Tomorrow, both Mrs. Hill and I are gone, and so you'll have a video. It's a flip video, but it's a video that you don't have to watch outside of school. We're going to watch it in school. Okay? We'll do that tomorrow, and you'll have a couple of worksheets today and tomorrow. Don't let me forget, you got a worksheet today. Wednesday, we'll go over that some more with some, and have some, like, lots of examples and doing all of this kind of a thing. And we'll do some more circular motion on Thursday. Friday, we'll probably do some kind of a Kahoot review or some kind of maybe an around the world review just to mix it up a little bit. And then what I want to really point out here is next week, Monday, a week from today, is your quote-unquote Chapter 4.1 test. Okay? We took Chapter 4 and we broke it up into a couple of mini chapters. Actually, I think we broke it up into 4 or 5 mini chapters. And so really we're taking kind of like a quiz, an over-glorified quiz, a quest. We're going to take a quest. Half quiz, half test. You know what I mean? Okay, so we're going to take a quest next week, Monday. Okay? So, it is a summative, yes. Yes. Okay? So, with that being said, let's dive into where we need to pick up on radian measures and converting, and more importantly, I want to talk about some additional degree measures. Now, you guys know that there's 360 degrees in a circle, okay? Or around a point, there's 360 degrees, okay? A couple other additional measures, because degrees can also have some subcategories, if you will, to them, which is another reason why I don't like them. Radians, they're just radians, and I like radians, okay? But degrees have all of these subcategories in them too. And what they're called is degrees, minutes, and seconds, okay? So 1 degree is also 60 minutes. Okay? Not just the TV show. Okay? 60 minutes, or if you wanted to write out, but each minute is also 60 seconds. Okay. So, 3,600 seconds is 1 degree. Because if each minute is 60 seconds, and each degree is 60 minutes, 60 times 60 is 3,600. Okay? So, you'll hear this referred to as DMS. Okay? Degrees, minutes, seconds. Okay? And so the book might ask you put it into DMS, or on a test we might ask you to take a decimal degree and put it in degrees, minutes, and seconds, or vice versa. Here is a degree, minutes, and seconds. We want to put it into a decimal degree. Okay, So on some of your calculators, I know on the old school TI-83s and TI-84s, it was DD and DMS, and then there was a key that had two arrows going both ways. And on the new ones, I don't know if it does degrees, if it has a conversion to degrees, minutes, and seconds or not. I have to figure it out. But if not, I'll show you the old school method of how to do it. Okay? So, this is 245 degrees. And to that, I'm going to add 10 minutes. Okay? Well, a minute, to get it into the same, is 60, or a degree I should say, is 60 minutes. Okay? So really, this 10 minutes is 10/60ths of a degree. Okay? So that is 245.167 degrees. And that would be the decimal form. Because 10 divided by 60 is the same as 1 divided by 6 is the same as 0.016 with the 6 repeating. Okay? So let's round to 3. Okay? Now, in one that has degrees, minutes, and seconds, so that's going to be 148 degrees, because that's whole degrees already, plus 16 minutes, well that's 16/60ths of a degree, plus 25 seconds, well 25 seconds is 25/3600ths of a degree. Okay. And when you do all of that on your calculators, you should get, rounded to 3 decimals, 148.274 degrees. YB? Okay. Yeah, but. Okay. Now, on the Inspires, it's relatively easy to do that calculation. On a regular calculator, you kind of got to do, you got to use parentheses a lot. Okay. So on that one, it would have been 16 in parentheses, 16 over 60. Plus, in another set of parentheses, 25 over 3,600, and then on top of all of that, plus 148. Okay? On the Inspires, come on now, you can just go 148 plus, and then you can make yourself a fraction, 16 over 60. Oops, tap the brakes, didn't go. 16 over 60 plus, make another fraction, what was it, 25 over 3,600. And then gets me right to there. Okay? So you can do that with the fractions. Or again, if you put it in parentheses, plus, open parentheses, 25 divided by, it's going to do the exact same thing. It's going to put it right in there for you. Okay? So, either way. Okay? Oops, that should have been 148, not 48, but. Okay? So, going the other way, expressing it as a degree, minutes, or seconds type of problem. Okay? So I know for a fact that my answer here is going to be 345 degrees. I know that. Okay? So I'm not even going to worry about that 345 part. I'm more concerned about the 0.12 of a degree. Okay? So let's first convert that into minutes. I shouldn't use X there. Let's use a dot. Then it's more mathematically sound. Okay? So what is 0.12 times 60? 7.2, and that's now in what? Minutes, correct? So this 7 is going to be my minutes. And now I'm done with that one. So now I'm more concerned about that 0.2. Did it again. And I'm going to multiply that by now seconds. I'm going to convert that 0.2 of a minute into seconds. And how many seconds do I get there then? Should be 12. So 365.12 degrees is 345.12 degrees is 345 minutes, degrees, 7 minutes, 12 seconds. See how we did that? Okay. What I'd like you to do now is I would like you to convert 215.63 degrees into DMS, degrees, minutes, and seconds. All right, so we know that it's going to be 215 degrees. Know that part. So 0.63 times 60 is going to be 37.8 minutes. So that tells me 37 minutes. And then 0.8 times 60 is going to be 48 seconds. So I get 215 degrees, 37 minutes, 48 seconds. There. Yes? Yes. Okay? So converting back and forth in degrees, in decimal degrees to degrees, minutes, and seconds. Okay? So, now, let's chat about the relationship between S, theta, and R. Okay? So, thinking back to the Smarty Lab, okay, does anybody remember what the relationship between the arc length S, the radius R, and the central angle theta is? Anybody remember?
Is it theta equals S over R?
Theta equals S divided by R? I like that one. Could it be another one? What if I wanted to solve for S instead of theta? So S equals R times theta. I like it. What if I wanted to solve for R? S over theta. Okay. Probably your easiest one to remember is the middle one. Okay. Your arc length is equal to the radius times the radians. And theta has to be in radians. Okay. That's the kicker. Theta has to be in radians.
Is that true for all of those?
Yes. Yep, all three of those, because they're all the same formula. Okay? So theta has to be in radians. So if theta's in degrees, you got to first convert it back into radians, like we did on Friday. Okay? Multiply by pi over 180, converts it into radians, and then you can use that formula. Okay? If it gives you what it is, but then asks for it in degrees, then you got to do some converting too. A little preview of things to come. Okay? So, a circle has a radius of 12 centimeters. What's that part? That is R. A central angle, theta, intercepts an arc length of 18 centimeters. What's that? That's S. Okay. Find the radian and degree measure. So how many answers do we need to have? 2 answers. Okay. So we want the theta one. So theta is going to equal S divided by R. So that's going to be S is 18. R is 12. So I get theta is 1.5 radians. Agree with that? Okay. Now, we need to convert 1.5 radians into degrees. So 1.5 radians times 180 degrees over pi radians. Oh, let's go to 3. Yeah, 3 seems to be a nice common number. Okay? So theta is also equal to what? So I would say 85.944. If I was going into decimal degrees, right? But what else could I put that into? Degrees, minutes, and seconds, right? So we would take this 0.944 or 9437, whatever you want, and multiply it by 60, and that would give us 56.62. 0.64? Okay. I didn't round mine, so that's why my numbers are probably going to be a little off, which is fine. So then 56 minutes, and then we'd take that 0.62 or 0.64, or whichever one you want, and we'd multiply that by another 60, and that would give us 38.4 or 37.2, either one. Okay, whichever one, wherever you're rounding. So we'll call that 37 seconds.
Is there ever a time you round the seconds, or you always just leave all the decimal places after?
I would round it to a whole number there. Yeah, because you're already out, to the 3600th of or 3600s, 3600ths. What I'm trying to say there of it. Yep.
Do you have to do that?
No, but it might ask you to. You know what I mean? So, because it's a little cleaner version, because then you're not rounding to a specific decimal, and you're rounding to a second. Okay. by a central angle of 2.5 radians in a circle of radius 8 inches. Okay? Which one do you want to use for that one? Of the three. Flashback. Which one do you want to use? The middle one?
S equals R times.
S equals R times theta, because I have here, I have my, go blue, okay, so that is my theta, and I have my radius, and I need to find S. So S is going to equal R times theta, so that's going to be 8 times 2.5. Because I'm in radians, I can use it as is. So what is 8 times 2.5? 20? 20? So my arc length here, whoa, what the heck happened there? Move you back. I love technology. We'll just erase it and write it again. So my arc length here is equal to 20 inches. 20 inches. Go for it. So we've got theta over here, but what's wrong with theta? Oops, wrong color. That's what's wrong with theta. Theta is in what? Theta is in degrees, not radians. So the first thing that we need to do is we need to go 60 degrees times pi over 180, or pi radians over 180 degrees. And so that gives us pi over 3 radians. Okay? So that's the first thing that we needed to do, because we have to be in radians in order to do that problem. Okay?
So do you not want to convert to actual decimals? You want to leave the pi?
Big fraction guy. Big fraction guy. Yep. And you will find that when we get into the unit circle and beyond, that fractions are just so much easier to work with. Yep. Okay? So we're again using our S equals theta times R, or R times theta, but now our theta is pi over 3, and our radius is 9 inches. So that's going to end up becoming an arc length of 3 pi, right? So preferably, I would give my arc length S here of 3 pi inches. Okay? That would be my preferred answer. Why? Because it's exact. It's not more exact, it is exact. Okay? That's the answer. Now, if you rounded that to, what would that be? What is 3 pi? 9 point what? Bless you. Okay? If you rounded it to 9.42 inches, I'd probably accept it. I wouldn't like it. But, okay. My rule of thumb has always been, if I'm going to use something later on in a problem, I want to keep it exact. Okay? And what we're building up to is what you'll learn tomorrow in the video with circular motion, where you're going to build off of all of this stuff. And so the more exact you keep it, the better. Okay? So that's my thoughts. So, at the Emory Sears track at Bluffton College, it has running lanes that are 1 meter wide. The inside radius of lane 1 is 33 meters. Okay? How much longer is the inside of lane 5 than the inside of lane 1 around turn 1? Okay? Now, there's a lot of things going on in that problem that we should probably talk about before we get into actually doing the problem. Okay? How many degrees is turn 1? Anybody in track here? Anybody ever seen track? Okay. The track looks like this, right? Except it's more exact, right? Okay. So turn 1 would be right there, right? So how many degrees is turn 1? 90 degrees. There's 4 turns to get yourself all the way around the circle, right? Okay? So if you take the straightaways out and you just scrunch that down, you get turn 1 is 90 degrees. Oops. Turn 2 is 90 degrees. Turn 3 is 90 degrees, and turn 4 is 90 degrees. Okay? In terms of radians, how many radians is 90 degrees? Pi over 2. Okay. So that helps us out here with turn 1. Okay. Now we need to know about lane 5 and lane 1. So we should find out the arc length of lane 1. So my theta for both of them is going to be pi over 2. Whoa, that kind of moved on me. What is the radius of lane 1? $33 meters. So that's going to end up being 33 pi over 2. Okay. Approximately, what is 33 pi over 2? What do you got? 51.84. And that's in meters, right? Okay. But now we got to go out to lane 5. So there's lane 1, right? And so this was 33. Then we've got lane 2, lane 3, lane 4, lane 5, right? And we want to go to the inside lane. So we're going to that lane right there, because that's the inside of lane 5, right? And each lane is 1 meter wide. So that adds 1, 2, 3, 4. So the radius of the inside of lane 5 is 37 meters. Oops, I should put a lowercase r there. So the arc length of lane 5 is going to be pi over 2 times 37 meters, which is 37 pi over 2, which is approximately What do you got?
58.12.
58.12. So what is my final answer to the question? How much longer is the lane marker for lane 5 than it is for lane 1? 6 point what? 6.28? Do we agree with 6.28? Which it's actually 2 pi. Yep, it actually is. Because if you subtract 37 pi over 2 minus 33 pi over 2, you get 4 pi over 2, which is 2 pi. Yes? Yes, you do have a worksheet. I should probably hand that out.